Welcome back to another lesson in AP Calculus. This is Lesson 5 from Unit 6. The title of today's lesson is Linear Approximations in Differentials. Differentials are going to become extremely important to us throughout the rest of the course. So we're going to introduce them here and look at a couple basic applications. We're going to start, though, with something closely related called linear approximations. So in a neighborhood around some point C, the tangent line to f at C approximates the values of f. So let's take a look at this picture to see what I mean. Suppose I have an equation f of x equals x squared sine x. And we know the tangent line to f at x equals pi over 2. What you can see is that in a neighborhood, and how far out we can go and still be somewhat accurate, of course, depends on the situation. But in this region here, you can see that the tangent line is almost identical to the function's curve. The curve is in blue. And you'll see because of the line thickness, you can see that it's hard to see the blue curve at all. It starts to appear right over here. And then at some point they become not a very good approximation. And then once we have this change in the curve of f to where it starts going back down, then it becomes a very bad approximation. But in this neighborhood here, it's a good approximation. So that's what we're talking about when we talk about tangent line approximations. In many calculus applications, the rate of change f may be known while the actual value remains unknown for f. So what I mean by that is we might well know what the rate of change is without actually knowing the equation. For example, you might know the velocity of a vehicle you're in without knowing its position function, and the position function might end up being too complicated to figure out anyway. And turns out we don't necessarily need to, because we can get, with much less work, a good enough answer using our tangent line. All right, let's take a look at an example. Let's say we're given f of x is equal to x squared plus 2. I'm sorry, it's just x squared. Write the equation of the tangent line to f at x equals 1. Okay, well, we've done that a lot. So let's go ahead and do that. So to find the equation of the tangent line, I need to get the slope at 1. So I'll take the derivative. All right. I'll evaluate the derivative at 1, which is 2. So my tangent line is going to be that. Okay. Now, what is f of 1? Well, f of 1 is just simply 1. So that's the point-slope form of our tangent line. But when we're using tangent line approximations, it makes more sense for us to go ahead and move this value over. And we can put it in the front or the back, but it gives us an answer like this: 1 plus 2 times x minus 1. And I love the way this kind of reads. It says that our approximation is that we're going to start at a y value of 1, and we're going to change by 2 centered around x equals 1. So it's a really nice way of looking at the equation. So let's use the tangent line from part A to approximate f of 1.01. Well, I think we can agree that 1.01 is definitely in the neighborhood of x equals 1. So I'll use this approximation symbol here. It's approximately the y-coordinate there. So I'll use my y-coordinate of my tangent line. So 1 plus 2 times 1.01 minus 1. And let's see here. I get 1 plus 2 times 0.01, which is 1.02. So this is a problem we could do very easily without a calculator. The x squared is not too bad, but you can imagine this would be a more challenging equation to evaluate. But you could see how we could be asked to do this on a non-calculator portion of the exam. But just for curiosity's sake, let's find the actual value of this function. So I'll just use a graphing calculator right quick. And let's plug it in. Probably could have done this by hand pretty easy, but this is fine. So f of 1.01. What is the value? It's 1.02.01. So f of 1.01 is equal to exactly 1.0201. Notice they're really close, but the actual value is a little bit above. It's a little bit above the estimate. And the reason why is because of the concavity of the function. Let's take a look at that graph right here. Let's take a look there. There it is. Let me make that a little bit darker. I like the projector mode there. So I'm going to graph the tangent line here. Y equals 1 plus 2 times x, was it minus 1? And we can see that our tangent line approximation, because this graph is concave up, it's always going to be a little bit above that tangent line since it's concave up on both sides in that neighborhood. So that's why we're a little bit below. All right, let's take a look at another example. Given f of x is equal to the natural log of x plus 1, use a tangent line approximation at x equals 0 to approximate f of 0.1. Well, what would this look like? Well, first we need a tangent line. So let's get the derivative. The derivative of natural log of u is u prime over u. So f prime of 0 is 1 over 1, which is 1. So we can write the equation of the tangent line. I do need to know what f of 0 is, though. That's equal to the natural log of 0 plus 1. Well, the natural log of 1, that's 0. So our equation is going to be y minus 0. I'll add it over. Y equals 0 plus 1 times x minus 0. Now that's pretty unsimplified, but I just kind of like seeing that whole story. I see that, okay, the y values on that tangent line start at 0. They're changing at a rate of 1, and it's centered around x equals 0. So despite how unsimplified that is, a lot of times we like writing it that way so we can see it, all the information. Or you can just simply say, it's y equals x. Okay, so let's use it to approximate f of 0.1. Well, so f of 0.1 is approximately 0.1 because y is equal to x. And let's take a look at the situation. So once again, I'm going to use my graphing calculator to take a look at, what was it, x? I think it was x plus 1, right? Yeah. So there's our graph, okay? We got a tangent line of y equals x. We could see that that was an accurate tangent line. So it looks like our tangent line must be overestimating because of the natural log being concave down. F of 0.1 is actually 0.0953. 0.095, of course, would round to 0.1 in the nearest tenth. So it's pretty close, within 5 thousandths of the correct value. All right, so we have a practice problem for you to use. I'd like you to use a tangent line approximation to approximate the cube root of 127. To do this, you need to figure out that the function we're talking about is the cube root of x. Find a tangent line at a perfect cube that's near 127. And then, just for information's sake, compare it to the actual to see how well we did. Okay, let's see how you did. So like we talked about, the equation that we're talking about is the cube root of x. Now, 125 is a perfect cube because the cube root of 125 is 5. So let's find f prime at 125. So I need to find f prime of x. This is x to the 1/3 power, right? So we'll bring down the power 1/3 x to the negative 2/3. And we'll evaluate that at 125. So that's 1 over 3 times 125 to the positive 2/3 if I move it down to the bottom. So when you're confronted with a situation like this, it's always better to do the root on the bottom. Remember, a fractional exponent, the power is the top, the root is the bottom. So the cube root of 125 is 5. 5 squared is 25. So again, we root it first to get 5 and then do the power of the top squared. It's much easier than squaring 125 and then trying to cube root that. And so that is 75. So 1/75. All right, so our tangent line, remember we got 5 as the starting value. We're saying it's going to go by 1/75 times x minus 5. Oh, excuse me, x minus 125 was the x value. So that means that f of 127 is approximately 5 plus 1/75 times 127 minus 125, which is 5 plus 2/75. And, we could probably try and get that into a decimal by hand if we were curious, but I'll just go ahead and type it in, because I want to know how we did. So that was 5 plus 2/75. So 5.0267 if we round it. The true value of 120 of f of 127, that's the cube root of 127. That is actually equal to 5.0265. So pretty darn close. Look at, to go all the way down to that decimal place. And remember, we round that up to a 7. It was actually 6. They were just off by a what was that, 1/10,000th. So very close approximation. All right, let's try another one. This time, let's use arc cosine of x. Use a tangent line to approximate f of 0.1, supposing that pi over 2 is approximately 1.57. I just gave you that so that we can try doing it without a calculator. Okay. All right, let's try this one now. We're going to need the derivative. The derivative of arc cosine u is negative u prime, so in this case 1, over the square root of 1 minus u squared. All right, so we're going to do f prime of 0.1. Oh, you know what? I'm doing that wrong. Let's not do that. We need to find the slope at a value that we know the arc cosine of close to 0.1. Well, that's 0. We need to find f prime as 0. And so that becomes negative 1 over the square root of 1, which is just negative 1. Okay, so the slope at 0 is 1. Well, what is f of 0? F of 0 is arc cosine of 0. So arc cosine of 0, when does cosine equal 0? That's when, on a unit circle that's right up here, that's when the cosine is 0 at pi over 2. So our tangent line is y minus pi over 2 equals negative 1 times x minus 0. And I'll move that over and we can get rid of the minus 0. And so it becomes pi over 2 minus x. But I notice that we were given that pi over 2 is 1.57. Just to kind of make this a little easier. So we can now tangent line approximate that f of 0.1 must be approximately 1.57 minus 0.1, which is 1.47. And let's see how accurate that is. So arc cosine of 0.1, 1.470 or 1.471, so really close. Okay, so given a function f of x, dy and dx are called the differentials, related to each other as follows, that dy is equal to the derivative f prime of x times dx. This is really just a simple algebraic manipulation of dy over dx. We said dy over dx is short for f prime of x. We've been saying that this for as long as we've been doing derivatives. So if that's true, if these infinitesimals, if they behave like the way we expect fractions to behave, that we could multiply both sides by dx. Now, it turns out the rules about why I can do that are slightly more complicated than just simply multiplying both sides by the denominator, but they work that way, and the notation was designed that way. So what we see is, what is this saying? This saying is that the change in y, the infinitesimally small change in y, is related to our derivative times the infinitesimally small change in x. So this value is dependent on how much the x changes and how much and what the derivative says you should change by. So when we'll oftentimes see differentials written this way. If we are trying to write the differential in terms of f of x, you'll sometimes see that df is equal to f prime times dx. So same thing. I just want you to be aware of that usually you'll see dy equals, something dx. You might see a df, and that's fine. It's just saying the rate of change of the function. All right. So let's find the differentials of each function. So it turns out this is really a relatively simple adjustment to our procedure. Just be aware of the vocabulary. It doesn't say the derivative, it says the differential. So the differential is dy. Now I'm going to take the derivative here, 10x dx. This might feel a little bit like when we were doing implicit differentiation, and it's very much so related. Instead of taking the dy over dx on both sides, I say I'm taking the differential, which we could write like this. So we could say I'm taking a differential of each side. The differential of y is dy. The differential of 5x squared is 10x, and then because of the chain rule, dx. So same kind of thing. All right, let's try this one here. So we can use the df notation. Is equal to 3x squared minus 8x, and then the constant goes away. And I'm just going to put that in parentheses, times dx. That's the differential. Also sometimes called simply the rate of change. Not the rate of change with respect to x, just the rate of change. All right, let's try this one. W, okay, so we know that's going to be dw. Then we got t squared e to the 0.2t, so we'll have to use our product rule, so 2t. And we could say dt right here, and then, have another dt later, but typically we don't do that. We'll just take the entire derivative first. So 2t is the derivative first, plus the second, which is t squared e to the 0.2t. So the derivative of e to the u is e to the u prime. So then times the 0.2. And I'll just put that whole thing in parentheses, dt. If we had done, if we had said that the derivative of t squared was 2t dt, we'd have a dt there, and we'd have a 0.2 dt, and we could factor out the dt, and it's the same answer. So there are many applications of differentials. One such application relies on the fact that for small changes in x, dy is approximately delta y. So when we switch from delta x to dx, what we're saying is we're switching from a non-inconsequential change in x to an infinitely small change in x. And if that small change in x is close to zero, it is really quite small, then delta x is basically a dx, meaning that the resulting delta y is basically a dy. So let's see how that works. Compare the value for dy and delta y for y equals sine of x squared plus 2 plus x as x changes from 1 to 1.02. So you can see we have a delta x there of 0.02. That is relatively small. So this example hopefully will demonstrate this relationship here. So let's find the delta y. Well, delta y is equal to the second y minus the first y, right? So the first y is when y is equal to 1. So I'll just say y of 1. And we'll use our calculator here. So we have sine of 1 squared plus 2 is 1.41. Oh, plus x, so 2.41. Let's get 3 decimals. 2.41, sorry. 2.141. All right, so there we go. And we're going to change that to y of 1.02. And I may have to go out and add more decimals here to get a... All right, well, that's a pretty big difference, I guess. So that's 1.121. And this was not a 2, this was a 1. I need to go back there and change that. Okay, there it is. So then our delta y is simply the difference between those two, which would make that a negative 0.02. Now, let's compare the dy value. So to find dy, what do? Well, dy is a differential, so we'll need to take the differential of each side. So dy is equal to the cosine of x squared plus 2 times the derivative of the inside is 2x plus 1. And that whole thing is times dx. So our dy is equal to the cosine. Well, our x value changes from 1 to 1.02. So I'm still going to put a 1 here. So that's an important thing to realize. We're talking about differential. We put, for x, we put the x that we're at when this process began. And then for the dx, we're going to put in the change. Okay? So if we're looking at x equals 1, we're starting there at some value, and we're looking at what happens as we move from there. And you get a slightly different answer if you do it the other way. Okay, so I'm gonna go ahead and calculate that. I'll just do that over here. Cosine of, that's 3 times 2 plus 1, and then that whole thing is going to be times 0.02. Okay, and so what I've got there is a negative 0.1959, which really rounds up to negative 0.0196. So let's do that. Negative 0.0196. So you can see that our dy here is a really good approximation for the actual delta y. This is the actual, and this was our predicted change. So it's similar to a tangent line approximation, but we're not approximating the true y value, we're approximating the true delta y, the true change in y. All right, let's take a look at another application. Suppose the radius for a circle increases from 10 to 10.1. We're going to use the differential dA to estimate the increase in the circle's area. So you can go through and find the actual change in the circle's area here, but let's pretend that we couldn't. For many problems, the calculations can be extremely difficult or impossible because we don't know the formula. Remember, we haven't really gotten there yet, but that's kind of coming. This idea that rates of change, but you don't have the information to get the full equation. So these kind of techniques become really important. Okay, so we're going to estimate the increase in the circle's area. So we'll start with the area formula. Area is pi r squared. Let's get a differential. So dA is equal to 2 pi r dr. In this interesting relationship that the differential of the area of a circle is equal to the circumference of the circle times the differential of the radius. So dA is equal to 2 pi the r. What did our r start at? Our r started at 10 times dr. The dr is 0.1. And so we end up with 10 times 0.1. That's just 1. So the answer is simply 2 pi meters squared. That is our approximation for the change in the area, 2 pi. All right, so I have a practice problem for you. You're probably going to need to use a calculator for this, but that's okay. Suppose the Earth were a perfect sphere. It's not. It's a little fatter at the equator. And determined its radius to be 3959 plus or minus 0.1 miles. So we're dealing here with a margin of error. What margin of error would the tolerance of 0.1 miles result in on the estimate of the Earth's circumference and its volume? The circumference formula for a sphere is 4 pi r squared. I'm not sure. Oh, that's not the circumference formula. That's the surface area. We're talking about circumference. So circumference around the equator, that'd just be 2 pi r. So go ahead and work those two problems and see what you get. Okay, so for circumference, the change in the circumference, the differential of the circumference is 2c times 2 pi, just simply dr. So if our radius is plus or minus 0.1, then our dr could be plus 0.1 or minus 0.1. So what that means is our estimate in our circumference is really only going to be, we're approximating with the differential. That's 6.28 times 0.1. Our 0.6283 miles. That means that, our estimate for the circumference at the equator in this situation, that's pretty accurate, right? We're guessing we're off by about 0.1 miles, but that means we're off up or down just a little bit more than that on the circumference. So let's take a look at what effect it has on the volume. I'll take the differential of the volume, so I get dV is equal to 4 pi r squared. Then dr. So our dV then is going to be 4 pi 3959 squared times 0.1. And again, it's going to be plus or minus that. So let's type that in. That's 4 pi times 3959 squared times 0.1. So, which gives me a dV value, of approximately plus or minus 196,96128.434 cubic miles. So that is an intense difference, right? Between the two. I mean, one of them was basically saying we had an absolutely correct, circumference. But let's take a look at what we're talking about here, like by looking at the actual different, dRs. So there's the volume of the Earth in miles. You see it's in scientific notation, that's a big number, right? So if we're talking about being off by a little bit, it doesn't seem to make that big a difference here, but you can see that within a few, these significant digits here, we're getting off. Well, this is if I change this scientific notation, then if I move the decimal back, it's going to a 10, then to an 8, then to a 7. So, you're talking about, a 10, a 9, 8, 7. So you can see how, 7 times 10 to the 7th would be in the tens of millions of cubic miles is when we're seeing that difference. So that's absolutely a correct kind of idea there. So big difference between the area and the volume and the circumference. All right. So, that's it for now. If you're now ready to watch a pretty cool clip, I recommend that you find the Simpsons episode Bart the Genius from the first full season of the Simpsons, way back in like 1989 or 1990. Watch it. Wonderful differentials joke. It's clever. You have to do the math to really confirm the right answer. So it's pretty amazing.